Thank you. I think I need to lower the screen. Lower the screen. Sorry, to lower the screen. It's here, right? No, the screen.
Oh, you need the screen, right?
Yeah.
Oh, okay. It's the okay. You're also done with this. I think if later just on the meeting, just turn off the screen lost.
Yeah. Okay, so yesterday when I finished my class, I still had an example to show, and so I think it makes sense if I recap where I was, close what I was discussing yesterday. So it was left in the middle, and then start today's lecture. Okay, so I was making this argument, okay, which is a definition, which is a way to I don't know, define, conceptualize the notion of natural and unnatural. And the idea, let me repeat it, is that you compute a quantity, an observable O. Is there a pointer? An observable O, general fact of life, and particularly in quantum mechanics, is that these observables are the contributions of result from the sum of several contributions. If you want, you can think abstractly of this as being different amplitudes in the sum of their histories. If you want, this could also be viewed as different histories, which depend in a different way on parameters. Okay? So overall, given a certain theory, a certain system, the system will depend on some parameters, which I indicate by the lambdas. And as I emphasized, it's always possible to view these parameters as transforming under some symmetries, okay? And so while these lambdas are the parameters of the theory, the CA are fixed, okay? So for instance, in the electroweak theory, the Yukawa, the gauge counting are the parameter, and when you compute something, you get the dependence of the parameter times coefficient that are unchangeable, okay? They are just determined from what the theory was, independent of the value of the individual parameter. So these are normally, okay, you can be more clever, understand whether there are pi's or stuff like that, but these are normally order 1 coefficients. Okay. So then the story is this, okay, there are all these contributions, and there are two situations that you can imagine happening. The first situation is where the resulting observable, in the result, there's no compensation, there's no cancellation between contributions that are not related one to the other by any symmetry that you can think of. Okay. In fact, if there are two contributions that are related by symmetry, you should group them together as a single individual contribution. Okay. So if the final result is of the order of magnitude or of the order of magnitude of what you would have guessed knowing these parameters, then you can say that this is a natural situation. Okay. And this happens in the vast majority of cases. Okay, that's what we call natural. On the other hand, the unnatural situation, which is less typical, is when there are where the final result is very much determined by what looks like an accidental cancellation or a curious, clever cancellation between contributions that are in no way related by symmetries. And these are the two situations that you can think of, and let me give you examples of I gave first an example of how this can be realized in how this is normally realized in laboratory practice, but I wanted to give you just a school book example of the first, okay? And why is it not moving? Yeah, and the typical example of a natural quantity is given by the pion mass in quantum chromodynamics. Let me give you the picture, okay? We have the usual picture, okay? There is a ultraviolet description in terms of quark gluons and the photon, okay? This is the standard model at energies just above the GV, okay? So remember, this is coming down from the weak scale, approximately scale invariant, then at the scale of 1 GV, the QCD coupling becomes strong, and bound states form out of quarks and gluons. And of course, as somebody yesterday was confused about whether things are controllable here, whether we can do computation. Yes, of course we do, because we know the microscopic theory. It's only a technical question to do computations here. Okay? So then the theory reemerges here in a new form, which is a theory of the only remaining virtually light or massless states. And this consists of the photon, which remains massless, and the so-called pseudo-Goldstone bosons, or the mesons, which focusing, for instance, just to make the discussion simpler, on two-flavor QCD, even though QCD has 3 flavors. These mesons are just the pi plus, pi minus, and pi zero, okay? And they happen to be light for reasons related to the fact that the theory per se at this scale is characterized to a good approximation by 4 couplings: QCD scale, the up and down quark masses, and the electromagnetic coupling. Now it turns out that in the limit where these 3 parameters are 0, the pions are Goldstone bosons associated with the spontaneous breaking of the chiral symmetry, SU2 cross SU2 down to isospin. Okay. Now it turns out that in reality these parameters are indeed small in a sense, which one can make clear. I mean, alpha is weak, okay, is a weak coupling, and these quark masses happen to be much smaller than the QCD scale. So in that sense, they're small. Okay. So because of that, the mesons are lighter than the scale where the transition happens. So below the scale, there emerges a theory, which is the theory of, you can think of the theory of the photon and the mesons. Okay. Of course, in reality here, there is also the muon and the electron, but for this discussion, I can forget about it. Of course, there's also the neutrinos. In fact, there's also the graviton, but let's focus on the things that are essential for the argument, okay? And anyway, all these other guys are very weakly coupled to So, of course, if you were coming from a poorer planet or a planet back in the evolution of science, on that planet, we would not just have the theory below 1 GV, okay? They wouldn't know that this would be your effective theory, okay? But we have done physics for the last 6 decades, and we know what's going on here, so we can see the transition, and we even have how powerful metals, lattice gauge theories, to really infer what happens, okay? To really compute what happens here to some significant amount of accuracy. So now, what is the story here? The story is, what is the quantity I want to focus on here? The quantity I want to focus on is the pi plus, pi zero mass difference, okay? So what is the story? So both pi plus and pi zero mass are determined, their being non-zero is determined by the existence of non-zero m up, m down, and alpha, okay? And so how what is the symmetry? And there is a symmetry that controls how these masses depend on these parameters. And the symmetry is chiral symmetry in the following way, okay? As usual, as I already emphasized several times, you can always view parameters as objects that transform under the symmetry. If you allow them formally to be quantities with suitable quantum numbers, then you restore the symmetry, and that allows you, by the argument I gave before, precisely the one that I gave for dimensional analysis for rotations, to track how these parameters enter into your observables. In the case at hand, let me tell you something that maybe, or I don't know whether you have already seen this, some of you have, maybe some haven't. The pions, okay, are Goldstone bosons, so they are essentially the Lie parameters of an SU2 matrix. Okay, they enter here. This pi is A is 1, 2, 3, sigma are the Pauli matrices, and now the story is that there is this chiral symmetry under which the quarks transform. Okay, under which the quarks transform. Is the chiral symmetry. There is the quark Qi is U and D. This is the doublet of quarks, and this is, you can do the mass matrices, something of this type. Now these are right or left if you want better, and these are right. Okay, plus emission conjugate. And now you can, if there wasn't this mass term, if there were just the kinetic term only involved the mixing of left with left bar and right with right bar. Okay, so you can rotate independently the left and the right quarks.
Can someone turn the camera? Thank you.
How do I turn on the camera? Sorry, guys. How do I turn on the camera?
Sorry, turn, not turn on.
Yeah. Sorry.
I can see your screen, but not the blackboard where you're writing. If it's too much of a problem, don't worry about it.
Yes, Sergey yesterday was using the remote.
We'll do it. Don't worry. Maybe I'll ask. Okay. Yeah. How can we turn on the camera? Because I'm also writing this.
Oh, so we just turn it off, right?
No. Well, sorry. I am
And I think
speaking
there's a
and
way of
writing.
rotating.
Is that not possible?
Rotating this.
It's already on. I mean, I can see it here.
Yeah, I can see the screen and I can see the view of the classroom, but it's pointed at the wrong blackboard.
You see me now? No.
Yes. It's just not pointed at the
Because
right
it's not
blackboard.
following me, the camera.
Exactly. Sorry.
Oh, I should have written here.
It's pointed at the blackboard on the left, I guess. Yeah, the one where you're standing
Yeah,
at.
so it's not that the camera is not turned on, it's not following me.
Yep.
It was.
Sorry.
Yeah.
I have no idea how to do it.
Okay, I'll do it here. Yeah, don't worry. But anyway, we will have to do it later. Anyway, when I will switch to the blackboard, somebody
Yeah, so
it should be a way, so it's better to solve it now.
I don't know, I never controlled this camera. Yeah, I mean, that's doing it. What they're seeing is this. So.
So I think Sergey was using this, right? Or this? No.
This is to control that, right? Automatically you put the number. But is the number follow you?
Sorry?
Is the camera follow you?
It seems so. So yesterday was following me the camera.
Yes, someone was moving it.
Someone was moving.
Sergey
Yes.
was doing it manually.
Oh yeah, it wasn't automatic.
Wait, listen up. So if you press 1 and then enter, it points at the left bottom blackboard. If you press 2 and then enter, it points at the right bottom blackboard. There you go. That's 5. That's a zoom out.
Does that work or need?
Did someone understand the instructions?
Yeah.
You did?
Yeah.
There we go. There we go.
Then you were enrolled or not?
That's
No.
perfect.
I can try.
So who can do it?
One in the enter and two in the enter, right? Yeah.
Just 1 and 2.
And then enter. But also you have pointed towards the camera.
Oh yeah.
Yep.
And go back to the and then
Okay.
So can you see what I'm writing here?
Guys,
Can you see
Yes,
what I'm
very
writing here?
thank you.
Thank you very much.
Yeah. Press 2 and enter. Yep.
It's not too dark, right?
Zero the other one. The other one.
It's not too dark, but now it's pointing at the left. There we go. Perfect. Perfect. Thank you.
So you can read here, right?
Yes.
It's not too crappy.
Yes.
Oh, good. Okay. Right. Crappy enough. Okay. So that's the deal. So this is the quark kinetic term. In fact, this is the covariant derivative. Okay. Of the fundamental microscopic theory. It consists of two parts. The real kinetic part, the one with derivatives, and the mass. The part with derivative, if I put the quarks in a doublet, which is a isospin doublet, both left and right. There are two doublets, left and right. Let me write it here, left and right. Okay? But you see that the derivative part is invariant under independent SU2 rotation of the left-handed quarks and the right-handed quarks, but the mass term is marrying them here, and however, you can view this mass as an external field or as a parameter that really transforms under the symmetry. So if when you do this, you also at the same time rotate the mass in the following way, then you have a symmetry. That means that in the low energy effective theory, if you have other fields that have some transformation property on this SU2 cross SU2 transformation, you can infer possible terms that the terms that are allowed in the Lagrangian, okay, that depends on those fields and on the mass, okay, and the way, and this is a story I'm telling you here. In the low energy theory, here I think I screwed up. I reflected everything in the mirror. Okay, that's okay. Right is left, left is right. Doesn't matter. Okay, at the end, I should have changed left and right there. I don't know. It's okay. So anyway, the field in the energy theory is the pion field. Is this object? It's actually a 2x2 matrix and transforms. And if you want, we can discuss that, but just take it for granted if you've never seen it. Transforms in the following way under the original symmetry, okay? And the mass transforms in the way I just said, okay? Now, okay, so these are the ingredient transformation of the field, transformation of the mass. Notice, and I forgot to tell you here, okay, that in this covariant derivative of the quarks, there is the gluon, but there is also the photon. And the coupling of the gluon is invariant under the symmetry, but the coupling of the photon isn't, okay? And again, in the coupling of, you can depict the coupling of the photon to the quarks in terms of a charge matrix. And the charge matrix is not commuting with these transformations, okay? And so now you can do exactly the same, like this mass matrix in general does not commute, but if you promote that charge matrix to essentially a field that transforms suitably under the symmetry, then you are in business. So the covariant derivative of the quarks maps in the energy theory to this covariant derivative for this field U. And the covariant derivative, as usual, there is the ordinary derivative, and there's the action of the charge. Now, it turns out that the charge acts left and right with in this form, 2/3 and minus 2/3, which is nothing but the charges of the quarks. Okay, so this is the way it acts on this field U. And now, if formally you promote, now U transforms under the symmetry, but now if you on the broken symmetry, because it's broken by this Q, but if you promote Q to say an object that transforms in this way, so now you have to differentiate Q acting on the left, Q acting on the right. In reality, at the end of the day, they are one equal minus the other. But now let's lift this particular point to a more general situation where these are independent. Okay, at the end of the day, we will take them at this value. But imagine they are independent. If they're independent and they transform in this independent way, one transforms with the matrix left dagger and the other right dagger, then you have a symmetry. So these are the ingredients with which you can infer the structure of the effective Lagrangian that arises at low energy for pions. Okay? And the story is this, what you get is this, okay? So to construct this Lagrangian, all you have to do is to use dimensional analysis and the symmetry, okay? So the first term is the kinetic term of the pion, okay? You have to write something which has two derivatives and is invariant. This is really invariant under the chiral symmetry because here there are derivatives, there are no mass parameters, and that's the only thing you can write down, okay? Now, this is two derivatives, this U has dimension 0, so here what is the only scale you can put is lambda QCD square. Again, this is, I'm applying dimensional analysis, which is the selection rules of dilatation. So again, in a sense, this is enforced by a symmetry under which lambda QCD transforms, okay? If you do scale transformations are broken by the presence, by the fact, say, so the theory up here was approximately scale invariant, but when you approach this point, a scale emerges, okay, and this scale invariance is broken. But if you formally treat this lambda QCD as a parameter that transforms under dilatation, again, you have the symmetry. So you're matching, but this is precisely like for the pendulum, okay? We are matching dimensionality. If you want to be clever, you can also infer that here there should be essentially 1 over 16 pi square, okay? And the reason for that is that is the principle I told you before. The theory at the scale lambda is strongly coupled. It's the scale where the quarks bind into hadrons. And you expect, and this is precisely the principle of NDA, that the bound state that emerge just below the QCD scale, at that very scale will also be strongly coupled. And if you fix this value here and you compute scattering of pions, you discover that this scattering becomes strong precisely around 1 GeV. In other words, you compute, for instance, the scattering phase of pions, and this phase becomes of order pi. So what is the natural unit of a phase? Pi, right? So when a phase is pi, means that you have gone 180 degrees around, so it's a big effect. So and this is how you fix this. And then you go on, okay? Then you start having terms that involve the breaking parameters. At the linear order in the quark mass, you can write this thing here, okay? This is a mass, this is also a mass scale. This should have a mass scale is the inverse of a length, so this goes, and remember, when you have the equation, you have d square equal m square, so derivatives and mass scale in the same way, okay? That's it, so you have this. Here it's a mistake, I'm a fool, here there should be a 1, okay, because this, then you go to second order, so this is the first order in the mass, you have this. Notice that this term here is precisely invariant under the symmetry I'm showing here, okay? If you now have the pion transforming in the suitable way, okay, it here transforms as v right, dagger, u left, okay, it transforms this way, then this term here is invariant. That's a simple thing. You can go, if you go to, and now you can go on and write terms with higher orders. At second order, you get this, and more and more. You also get this other term. So this is due to the quark masses, but you also get a term coming from the fact that, remember, you had those charge matrices that transform under chiral symmetry, and putting those matrices together, you can concoct this term. This term is also formally invariant. Now, these Q's enter together with E, okay, so whenever you have a Q, you also have an E, okay, so then you have an E square here, and if you're clever, you can also infer that there is a 16 pi square here. Why? Can anyone guess how to say that it should be like that? Let's see whether you can play these little games. So you know that, let's say the one way you can argue is this. In the limit where, in the ideal limit where electromagnetism is as strong as the QCD, then the effective electromagnetism should be of the same order as the genuine QCD effects. They should show no suppression. Okay. So what is the limit where electromagnetism is strongly coupled? Is the limit where as I said the other day, E is of order 4 pi, because as you know, the expansion parameter of QED is not E squared, but it's actually E squared over 16 pi squared. So then you say that here there should be a coefficient such that when electromagnetism is strongly coupled, this term is as important as those. In other words, it features no suppression on the scale, on scales of order lambda QC. And this is how you fix it. So that's it. You are basically, so now up to coefficients C2, C3, and C4, which are respectively order 1, and you can only compute if you solve the theory exactly, let's say of the lattice, you basically have a picture for what's going on. And now you can compute, you see, now you can compute the meson spectrum as a function of this unknown order 1 coefficient, but the big dependence on the small parameters is there. So particularly at the leading order, this is the leading term, the term that dominates, okay? And it turns out that if you look at, for reason again of group theory that you can see easily, this term gives the same mass to the pi plus and pi 0. Okay? Even though up and down quark are not degenerate, it turns out that they enter in both cases, for both mesons this way, and this is not split. So at lowest order, and this is responsible essentially for the observed mass of the pions, which is about 135 MeV. If you put here the mass of the next heavier hadron, which is, say, the rho, you deduce that this mass here is about, this sum here is about 10 MeV. Okay, that's a quick way to see what the masses of quarks are. But then, if you go to subleading order, so now at this order, pi plus and pi 0 are the same mass, and the splitting only comes from the higher order. And it comes from these two terms, okay? One term which depends on MQ, and one term that depends on alpha. So MQ and alpha, from the point of view of the physics that we understand right now, are completely independent parameters. Okay? In the standard model, one is a gauge coupling, and the other core masses are coming from Yukawa coupling. They involve the web of the Higgs. It's maybe in string theory there is a very clever way of seeing that there is a correlation, but not at this stage. Okay, so they're independent parameters, and they both contribute to the pi plus pi 0 mass difference, and in the following form. And it turns out that this term dominates, this term is subdominant, and there's no cancellation. Okay, this is all to tell you that in principle this C3 could have been. I don't even know whether this is positive or negative, but I can imagine a situation where this is negative in other systems. And it's imaginable to, I can think, in fact, this is what we do for compositics, of situations where there are two different contributions like this, and this compensates that to the arbitrary level that you want, okay? You could even compensate it exactly, okay? That would be a tuned situation, okay? But in order to achieve that, we would need some guy, okay, either it happens, if it happens, it's truly mysterious, or if it happens, it's really mysterious, and it really points to something that we don't understand. Of course, if you have a cancellation of 1 in 10, no, 1 in 100, perhaps more, but if you start getting several orders of magnitude of compensation, I think the nose of a scientist, that's something I should understand, right? It's like the Lord is not playing dice here, okay? And so this is the example, and this is responsible for the what? For the about 3 MeV mass difference between the pion and the pi plus and pi 0. Notice that there is a similar game that you can play for proton and neutron. Are you aware of that? There it's much more puzzling what happens, but I will tell you later, okay? Puzzling in the philosophical sense.
Sorry,
But,
Riccardo.
yeah.
So here there are two different contributions. We are both breaking isospeed.
Yes.
We are comparing those two.
Yes.
So what if there is only one source? I mean, how
If
does
there's only one source, then then it's hard to, then it's
Then
hard
it's
to,
like
then,
inspection
then you
rules and
cannot
that.
tune, yes. Well, there's only one source. It could happen that the coefficient is tiny for reasons that, in that particular theory, but then in all theory, I mean, in all variants of the theory with this, you vary alpha, they will always be small. Again. But then, if in the particular theory this is very, very small, then you ought to understand it, right? Normally there is an explanation. Of course, if it's 10 to the minus 1 to the... There are examples in the Pion-Lagrangian where we have these accidents, like the delta I equal 1/2 rule, but these are all effects in 1 in 20. These things happen, okay? But if you start getting 10 orders of magnitude, I mean, we want to understand things, right? We don't just accept everything. Okay. So, notice that this, and this is important, notice that I could have guessed this contribution, well, because this contribution, you see, it has to do with it's of order lambda QCD, so it's clearly coming from what happens. It's of order lambda QCD, so it's clearly coming from effects at this scale, okay? At the transition between one description and the other, it's coming precisely from the physics of confinement. But yet, you could have estimated that there is an effect like that also by just working in the low energy effective theory. Let's say you are the guy in the poor planet where you've never seen QCD, you're just doing pions, okay? It's precisely the situation where there's why I insist in this situation where you have not explored higher energy, because that's precisely the situation where we are in the standard model. We're using these examples where we knew the energy effective theory, and then at a certain point we learned about what happens above, to get intuition for what could happen at shorter scale than what we have explored in present experiments, okay? Of course, things can be different, okay? But that's the only thing we can do, right? We don't have other perspective at the moment, okay? But so it's important to think about what would, let's say you have a guy who only has this effective Lagrangian, okay, hasn't yet explored that, and the guy measures the pi plus pi zero mass difference, okay, and finds, it measures and it finds that it matches essentially this, okay, with the coefficient here over the 1. And then the question is, does this make sense, okay? Or am I surprised from the point of view of a low energy guy, okay? Well, in the low energy theory, and this is what we normally do when we talk about the Higgs mass, in the low energy theory, the guy could have attempted a computation of the pi plus pi zero mass difference, okay? At least the electromagnetic contribution. Well, because in the low energy theory, there are photon interactions, okay? The pi plus is coupled to the photon in the standard way. This is the leading order. This is the standard coupling of pi of a scalar, charge scalar to a photon that you have in scalar electrodynamics, okay? And notice that this is only for pi plus, there's no such coupling for pi zero. Pi zero is neutral, okay? Doesn't have a photon coupling. So then you can, okay, there are these coupling. Now I can start doing perturbation theory, compute the correction to the propagation of pi plus. There are these two diagrams that, among other things, they give you a correction to the pi plus mass, okay? Correction has this form, okay, modulo order 1. Here it's actually something like that. So it's E squared times the loop integral, and alas, the loop integral is divergent in the UV, so you cannot, it's not, what does it mean? It means that this contribution is not something that you can compute in the effective theory. It's something it is dominated, these two diagrams measure quantum fluctuations are dominated in the UV. But what is the UV for this guy? Well, it's the cutoff where the description breaks into another one. And the guy may not know yet where this description breaks down, okay? But the guy can say, well, okay, if this breaks down some scale lambda, which some putative UV scale, then this will give me a contribution here to the pi plus mass, which therefore is the two pi plus pi zero mass difference, because pi zero doesn't get any contribution, which scales like this in terms of the UV scale. Okay, and notice that with this naive estimate, this is precisely the up to order 1 effects, what I was showing before, right? So in a sense, by doing this naive computation, which is, say, computing the quadratic divergent correction to the pion mass, and using an unknown UV scale, here, take away QCD, say this is some unknown UV scale for the guy, which dominates where the thing gets cut off because the description changes, and presumably the guy says, well, above this scale, let's say the pion maybe is composite, so that quantum fluctuations. So the pion, if this composite is like a ball, okay, and this is the sensitivity of this particle to quantum fluctuations, but if the object has a finite size, it won't see fluctuations that are shorter than its size. It will see fluctuations that are longer, okay, and if the size is 1/λ, okay, you have to cut this off at lambda, and you get this result, okay? And then you compare this to what the guy observes, and the guy deduces that the scale where things break down is 1 GeV, which is correct, okay? So this is normally what we do, as we'll see later when we discuss the Higgs mass. And you see, what is the deal about this result? Well, the deal, why this result is still meaningful, is that this result is just embodying all the selection rules. There are two selection rules that enter in this formula, okay? One is the dependence on the parameter that breaks isospin, that is the charge, which in a sense, when you compute this loop, you're essentially computing this term, okay? The structure that you're computing is that. And the other is the matching of the quantum number of dilatation, which is dimensional analysis. Okay? So this formula here is in no way different than the formula where you estimate the frequency of the pendulum. You have the frequency of the pendulum is number of order 1, okay, which here I don't indicate, times the square root of G over L. Okay? And square root of G over square root of L are fixed by dilatations under of space and time, okay? And here you have two factors, you don't have a ratio, you have two factors, and the dependence is fixed by two other types of symmetry. One is dilatations, okay, which is dimensional analysis, and the other is isospin, okay? So this is just to tell you that all this, and all these things that we do every day when we do computations in field theory, like of quantity like that, and then we do estimates, they are in no way different than the way of inferring the results that you learn in physics 1, right? Dimensional analysis. There's nothing more sophisticated, than nothing even shallower than that, because dimensional analysis is deep, if you think about it, okay? So it's really the basics. And then, of course, that's the example of a natural situation, while then I presented this other example, which is an example of an unnatural situation, where and situation like this in the lab practice, situation where you can have an arbitrarily tuned result for an observable normally arises when we have many choices, okay? And this I already explained, right? This was the example of the antiferromagnet, and the story is that this antiferromagnet, okay, this is the example, okay, is a crystal, okay, and the crystal has essentially a continuum parameter that is the pressure under which you can create it. I mean, you can put it in a device and you change the pressure. And now the low energy observable, so you have a microscopic crystal, and now you compute, or you measure the macroscopic observable that come in this crystal. Well, these observables are functions of some parameters, okay, of course, they're functions of the parameters of atomic physics, the alpha, an electron, also maybe some spin orbit, there are other things, okay, and maybe also the proton masses, of course, but that's it, okay. But then there is this external parameter that depends on the state, because in condensed matter you also have parameters that control how you created this object, what type of recipe you follow is like cooking, right? And the recipe parameter here is pressure, okay? And it turns out it's continuum parameter. And as I said, when there is a continuum parameter, there are possibilities at some point of having peculiar behaviors. And in this particular case, the peculiar behavior is the one where the first order term in the potential, which you call the mass, changes sign. Okay? At the point where precisely changes sign, the mass is 0, you have an exactly massless degree of freedom. Okay? In fact, you have 3 massless degrees of freedom there. Okay? Because this is a triplet, and you have what is known as this is a conformal field theory, if you want, at this point. Okay, in this particular case, it becomes free because this coupling is a Portic coupling in a 5⁴ theory, and as you know, it runs to 0 in the far infrared logarithmically. This is just the computation in 5⁴. So essentially, at the point where p is equal to pc, the long distance description is 3 free scalars at very, very long distance, at distances that go to infinity. Of course, you will need an infinite crystal for that. At the left and the right of this point, you have either a paramagnetic or a nil phase. But this specific point is a point of measure 0 in the space of parameters, and that's this specific case. Now, so this situation, which is attainable in laboratory, it's understandable that we expect it to be not typical and in fact unexpected when we don't have this option. Okay, and this is what led Toft to formulate the notion of naturalness, which I will now discuss in more detail. Okay, I can now stop this and go back to the blackboard. Any questions? Okay, let me disconnect this. Let me bring this up. No questions? Who has never seen pions? Don't be ashamed. How many people have never seen pions?
For real or on the blackboard?
This reminds me, I don't know why, for some reason, this reminds me another thing. When I did my exam at the end of the first year of grad school about quarks, there was Barbieri in the committee, and they asked me whether they had already seen quarks, and they said no. Barbieri got so pissed. They've seen them, jets, and so yeah, seeing you never heard about pions and how the work goes to bosons, right?
Oh no, I just never calculated processes in QED with pions.
Sorry?
No, I just never calculated QED processes with pions.
But you know what pions are?
Yeah.
Okay, that's okay. You don't need to compute. I also never compute. All the computation I do is this little shit you have seen. I don't get beyond that level of technicality. You do what you can do, right? You do what you can do. There are people who are very good and can do very technical differently, and there are people that do this qualitative, squeaky stuff. Okay.
At the level of exploring the landscape of possibilities for things getting smaller or large, if one changes NC and make it very large, does the story for pions change? In terms of selection rules.
No. I don't think so. In that case, because it's overall NC. Good question. I don't think so at this level, no, because the number of f-pi's is the same, so it's a good question. I don't think this thing changes.
I think eta prime becomes
Because n changes the trilinears, but this is
eta prime becomes like.
Sure. Okay. Okay. You're saying that you could have a mix with eta prime. You could have pi 0 and eta prime mix, and that maybe changes something. Right. That's possible. So you're saying, I don't know how to answer this question. Is there an N
And depends.
where something
Yeah.
weird happens?
For instance, the mass splitting, no, since the electromagnetic contribution is just like one.
Yeah. Notice that even N is discrete, right? So there could happen something crazy at N equal infinity. Oh, that would be very weird. So then it must happen some finite N. It will happen some finite N, so it will have a precision of 1 over N. You can probably get when you go from N to N plus 1, then the thing does no longer cancels, but this will not be a cancellation better than 1 over N. Is this clear? Yes.
Yeah, I'm just saying.
That's the fineness. It's like Busso-Polchinski. How fine can you get the?
But yeah, my comment was the electromagnetic contribution is just now coming from one gauge boson, whereas there's so many gluons that contribute.
But if you do if I'm thinking of the NDA, the change of N just changes the per factor. Instead of being 1 over 4 pi square, it's N over 16 pi. Instead of being 1 over 16 pi square, it's N over 16 pi square. And it's factored out at this level, it shouldn't matter. If you change the number of flavors, that's a different story. Okay, but that's okay. Let me erase this. So what I want to discuss now is, in more detail, the notion of top naturalness. So we've already seen, okay, the way presented the notion of natural is by considering abstractly a theory with some parameters, the lambdas. In this theory, I compute an observable O, and this observable O is the sum of several contributions from several amplitudes. So I went directly from the parameters of the theory to the observable. On the other hand, in the two examples I presented, certainly in the case of QCD, this situation was presented as a two-stage two-stage procedure. There's a microscopic theory, which in the case of the pion is QCD, and I am computing some low energy observable, which happens to be the pi plus pi 0 mass difference, which is also just a coefficient in low energy effective Lagrange. Okay, so in a sense, I can. So and then with this pi plus pi 0 mass difference, I can compute the propagation of pions, I can compute observables in the low energy effective theory, but it's just a term in the Lagrange. So in other words, I go from the microscopic Lagrangian to the coefficient in the low energy effective Lagrangian, and then observables. So these are the two steps. And rather than going directly to observables. Okay. So in a sense, you can also just stop at the first step and say, look, let's consider the dependence of let's say, let's just consider the first step where we have the microphysics parameters with which we compute the parameters of the energy effective theory of the macrophysics, and those are essentially already a proxy for our observables, right? Because then our observables in the energy experiment will be functions of this. Okay. So the idea is this: we have some scale lambda, very much like in QCD, where here we have the microphysics. Here we have the macrophysics, the energy effective theory. And if you want to think concretely, really think in terms of this example of QCD and the pions, okay? In fact, normally when we think of a situation where we have some strong coupling, some microscopic, we always think of QCD, okay? Unfortunately, we don't have that many examples of it, but it's amazing how rich QCD is. It has pretty much everything. So I think it's good to use it. And there are even more things that can be said about what happens around the 1 GeV. I think studying what happens from 5 GeV down gets you, let's say, 70 or 80% of all of particle physics. Okay, so what you have? You have some microscopic parameters which are indicated by GA. I indicate them as capital, indicating that these are more important because they are in a reductionistic viewpoint, they are describing the truth at shorter distances. And once you know things at shorter distances, if you're clever enough, you can compute things at longer distances. But rather than going and compute them directly from here, you can do it in 2 steps. You can derive a low energy effective Lagrangian valid below this scale. So this is, if you want, that's the fundamental Lagrangian, and this is the EFT. And these are parameters of the EFT, and these are parameters of the fundamental Lagrangian. Okay? In our case before, this was there was here alpha, the mass of the quarks, and alpha. And here we have, again, alpha, it goes without saying, but we have the mass of the pions, lambda QCD, and several other quantities. Okay? The Lagrangian for pions, I only wrote the first terms. It goes, as always with the effective Lagrangian, it goes up to infinitely many derivatives. Okay? And as long as you have an energy lower than lambda QCD, this expansion is convergent. So what we have here, we have this GI. Now, these GI are, very much like before, are computed by integrating out this short distance physics. Of course, there's some fuzziness of how you define this procedure. There are different procedures, there are different schemes if you can follow, but the story is always the same. These GIs are going to be functions of the capital GA. Okay, they're going to depend on them, and like for all amplitudes that I've shown, for all physical quantities you can think of, they satisfy, this relation here satisfies selection rules. Okay, particular dimensional analysis, symmetries, the analog of isospin. Okay, so I can always think of symmetries under which the coupling is transformed, and this will satisfy selection rules. Okay, and again, we expect, and we can always be wrong, okay, but we expect in a physical situation where there is no lab technician fiddling with in detail how this thing works, we expect this mapping here to satisfy naturalness, at least to some level, not to violate it in a dramatic way. Notice that from the point of view of principles of physics, it could happen that there is an extreme fine-tuning unnatural in this mapping. It can happen. This is why, if you want, these all arguments are sometimes say, oh, you guys are doing philosophy. Okay. If you think that this is just philosophy, there's no effort I can make to try to convince you. Okay. This is just a question of how you feel. What are what do you think is a good question? What do you think it's a mystery that is worth worrying about at night? Okay. And accidents that we don't, things that look like accident, if you like Sherlock Holmes, normally you want to dig and understand, okay? And maybe at the end it's just an accident, but they're worth spending time and trying to figure out. So then, in view of that, Toft made this into a principle, saying that in fundamental theory, in theories of particle physics, extremely unnatural situation for this mapping do not happen. Okay, okay. These things do not happen, and normally this mapping, and you set it turned it into a principle that this mapping should respect naturalness. Should be in the first case. There should not be cancellation between parameters that have different that are different and not related by signatures. Okay, and that's a principle. But then the question is, but in order to figure this out, I need to know these guys, right? Because right? This is what the relation is. While normally, when we, in a sense, I did not present it this way. This is my representation of what he's saying. But let me go ahead. I will get to the way he's saying it. I believe this is in a sense, it's a more complete way to present it. Not more logical, but more complete. So, on the other hand, we are always, and that's the interest of physics, we are always in need of knowing what's going on here. Normally, we are always at the edge of physics. We know physics up to roughly here, okay, or whatever. We only know the low energy theory. We don't know the GA. The GA is at best an hypothesis. We know the GI. And then the question is, I mean, okay, how can we decide if the low energy effective theory that we are here, whether the GI here, satisfy a natural relation with the fundamental parameters? Is this clear what I'm saying? If we don't have them, how can we do that? Okay. So it's interesting to know, right? If the standard model or any other situation we may encounter, whether that situation is natural or not, okay? And the way I presented it here, it seems like you need to know the microphysics. But actually that is not true, okay? In the following way, you can think of the following reverse or tricky argument, okay? So imagine you are here, you have measured these parameters, okay? You have done your experiments, and then the question is, how do I know whether this is a natural situation or what? How do I know whether this theory that emerged here was concocted in a clever way by the theory above, in a way that goes beyond selection rules and dimensional analysis, in a way where there are relations that are cannot be understood purely in terms of symmetry, selection rules. And well, you can argue the following way, and that's essentially always the case. Take, for instance, one of these couplings, take the first one. In general, you can write expressions, okay? Let me see whether I write it in the same way. I just want to make sure that I'm not, so sometimes I have a better way to. Okay. You can write this in terms of some, yeah, maybe here I should say GI. Okay, it's the GI of GA, okay? I think it's a better way of saying things and of writing things. And so given, there's going to be a collection of them. In fact, there's going to be an infinity of them. But when you're at low energy, at any given order in the derivative expansion, you have a finite number of them, okay? So let's consider the first one, for instance, or one of the first ones. And it's often the case, it's normally always the case, that you can think of some expression, let's say I1, of all the other GI, I different than I1, okay? So single out one coupling, and then consider all the other ones, okay? You can often write an expression for the remaining ones. Sorry, I'm not being clear here. Let's say you have n coupling, take the first, and then you have another n minus 1. You can often write an expression, and normally in the relevant case, the expression is always a monomial or something like that. In some situation, you can have some inverse powers of some coupling. Maybe the coupling is a mass or something like that. But inverse powers of couplings are normally not appearing because you expect that your description should be smooth when the coupling goes to 0, so nothing crazy should happen. So then it's better you don't consider inverse powers, okay? So, but anyway, let's say you can, and you will see examples in a moment of what I mean. So normally this is a monomial, is an expression, it's a monomial expression in the couplings, such that, and I indicated this way, they transform in the same way. Such that this relation satisfies selection rules. Okay? So imagine you can do that, okay? Imagine you'll be able to concoct that. One there's an expression of n minus 1 that transforms precisely like this one. The square here doesn't mean that they are equal, it just means that they transform in the same way, okay? Is this clear? But then, you know that this, in reality, these GI are themselves function of the GA. So, this expression here is GI of GA. So it's some expression, or it's some function of the GA. So it's an expression that you can potentially have here. It's just one of the contributions that can appear here. Okay, you can imagine that in the fundamental theory, these GI are the sum of several contributions. Okay, very much like in the usual case. Okay, the way I said it, GI is the sum of several contributions. Okay, to this. Each of one have a different dependence on the fundamental parameters, and fine-tuning is just a situation where they compensate. Okay, so what you have concocted here is an object which is written purely in terms of the GI of the low energy parameters, but in reality, in any physical situation, this will be itself a function of the fundamental. I'm not saying anything deep; it's pretty trivial. Now, if however, now in the physical situation, now you can construct several of this, okay? And so you expect that in the mapping, a relation like this, contribution like this here can exist, okay? Contribution like that can exist. And here you're essentially, you're computing expressly, and this contribution here is just equal to something pure in terms of the low energy ones. So in other words, what I'm saying is that if in reality, what you find is that GI is much, much less than this, okay, of one of these, of the maximum of this contribution, then clearly, given that this contribution is indeed something like that can appear there must have been a cancellation in the mapping between the UV and the IR. So in other words, you can set certainly a necessary condition. In fact, turns out it's also sufficient general grounds in practice, but certainly logically it's necessary. A necessary condition for not having had any big ununderstood cancellation in the mapping between the UV and the R is that whatever object you can write with low energy couplings, okay, with n minus one of them, okay, which can represent a potential contribution to the nth one, to the other one, should satisfy this condition. Okay, it should not be much smaller. Okay, is this clear what I'm saying?
I think we all need a concrete example.
We will get to the concrete examples in a second. Okay? Oh, because you prefer always concrete.
No,
Yeah, you already. Alberto keeps saying that I have the wrong strategy. First I give the general logic and then the example. I should do the other way. Maybe you're right. Okay.
I said it once.
You said it once. But it resonated in my head for the whole day. Whatever you say it once, and Alberto said this, so I keep saying you. I haven't dreamt you say you should say it exactly. So so that's a little trick, okay? So then what is the story? So then we are ready to. So this tells you that the low energy parameters, okay, the structure of the low energy parameters of the theory must satisfy some internal consistency, okay? If, for instance, n minus one of them are there, they're non-zero, okay? And you can concoct an expression for this n minus one out of this n minus one that matches the transformation property of GI1. Then it's clear that if GY1 were to go to 0, you would have an unnatural situation, okay? Because there exists the set of parameters that you have that are non-zero indicate that in the mapping from the UV to the IR, there are contributions that are non-zero to this guy here. But if this guy is 0, I mean, yeah, that means that there have been big cancellations, okay? Because the existence of this non-zero contribution indicates that in the mapping there are contributions. If the result is exactly 0, it means there has been complete cancellation. So the way Toft stated this is much simpler if you want, is that the theory is stated in the following way, is stated, okay, let me say it this way. So the fact that there are contributions, that you can write contribution to this object, and this object is zero, means that the symmetry under which this guy transforms is broken. Okay? Verify that you can write something that transforms like this guy means that the corresponding symmetries are broken by these parameters, okay? Because these parameters together can concoct an object transform precisely like this guy, okay? So then Toft simply stated the principle in the following way. In a natural situation, okay, a natural situation is so let me say that. In a natural situation, okay, you have a natural situation only when, in the situation where when the parameter goes to zero, you recover an exact symmetry. Okay, so in this case here, if I send gi to zero, I don't recover any symmetry because that symmetry is broken by these other guys. Okay, so Toft stated all this bullshit that I'm saying in a much simpler way, but of course, without getting into the complete logic. This is why this is often seen as debatable. I'm going through the process of how this you can get to that, just to try to make it look less out of this world. Okay, it's a at the end of the day is the pendulum. Okay, there's nothing more than that. So anyway, but if the situation where this is zero, and it being zero does not increase the symmetry, is the one where there are other contributions, that there are other terms that can contribute to it. Okay? This situation is what Toft calls unnatural. Okay? So essentially Toft expresses the notion of naturalness.
So there's a question.
Yes.
Sorry, just to make sure I understand here, if I take what you say and then phrase it a slightly different way, the opposite way, that if I increase the number of parameters, so I turn one parameter on, turn it from zero to non-zero, then that would decrease the symmetry. So if I add an interaction term somehow, there is always a symmetry that is no longer there. Doesn't seem...
No, let me put it this way. Let me say it perhaps in a different way.
Yeah.
In a natural situation, when this goes to zero, also these other guys, some of these other guys should go to zero, in such a way that this contribution doesn't exist. So they should go to zero in such a way that you cannot build an invariant, an object transformed precisely that way. Okay. In that case, you have exactly the same.
So say if we have like if we just have a lot of operators and like 3 of them respect some SU2 symmetry.
We will see examples. I think it's probably better if we go to I think right. I think the examples will become more clear. Okay, so now this is cleverly stated. Okay, I think this is more quantitative, however. Okay, here you can there's a way to infer how off you are from this ideal situation, from this natural situation. Okay, because I can quantify. I can say, okay, let's say that this guy is less than this. I can say at what value. Okay, at what value can I start seeing that things are unnatural? Okay, I don't need to go exactly to zero before that. Okay, So this allows you to quantify it better. And let me give you examples, okay? Let me give you examples that are probably better than just talking. Okay? First example is a simple theory with two fermions. Okay, you're familiar with wide fermions, right? Two-dimensional spinors rather than Dirac. Has everybody seen wide spinors? Right, because Dirac spinors, the basic units are wide spinors, okay? You should forbid to teach the Dirac fermion to start with. This is forbidden in the 21st century. Okay? So let's say you have two spinors, U1, U2, I call them like neutrinos, and they have the bar is sigma mu, okay, U1 plus I U2 bar sigma bar U2. And let's say there's also a scalar, and then there are some interactions, okay? The scalar may have its own potential, doesn't matter the scalar, it's a real scalar, okay? And then there are Yukawa interactions. There is a phi G11 U1 U1 plus G12 U1 U2 plus G22 U2 U2. Okay, so these are Yukawa interaction of all these types. Okay, and you can think of chiral symmetries. You can think more symmetry. You can always have more symmetries than the one I'm talking about. Okay? You can also rotate them, but for the sake of what I'm discussing now, it's sufficient to consider just this rotation. Just the independent phase rotations of these two fields, okay? And of course, phi doesn't transform; is a real field. And of course, the symmetries are broken by the Yukawa interactions. Okay, these are chiral symmetries. Okay, so they're broken. Okay, so you have U. So this is U1 1, and this is U1 2. Okay, and then you can write here how things transform under this. Under the symmetry. Okay, sorry. So U1, U2, but you can also sign, so U1 is 1, 0, 0, 1. These are the charges, okay? These are the charges, Q1, Q2. This rotates with unit charge. It doesn't rotate under 2, so it has 0 charge. Okay? And of course, these two rotations are broken by the Yukawas, but you can formally restore the invariance by assigning the Yukawas transformation properties. Okay, G11 has charge -2. Okay, if U11 rotates with charge 1, 1, if this has charge -2, it compensates. Of course, there should also be the Hermitian conjugate here, right? Okay, I forgot to write the Hermitian conjugate because there should be the power. Okay. And G11 has 0 charge under Q2 because there's no Q2. G12 has charge -1, -1 under each of the U1s, and G22 is the other way around. It has 0 charge under U11 and -2. And now, okay, you can ask yourself, okay, imagine this theory is emerging, is an effective theory emerging some high scale lambda from some more fundamental theory. It's always like that, okay? At a certain point we will deal with quantum gravity, but at a certain point, I don't know when, okay? But for a very long time we will be doing this, okay? So, so these parameters, so these guys will all be thought, should all be thought as function of parameters of fundamental theory. Okay. one thing, now let's play the game here. Let me give you an example of this, okay? Of how to build an object out of the others. So let's pick G11 as our guy that we single out. G11, okay? What can we build that matches its quantum numbers? Let's see whether, and then we take a 5 minutes break. Is that okay? A monomial, right? So what you have to build is a monomial out of the other two, G12 and G22, that match the quantum numbers, okay? So G11 has charge -2. The other guys, G22 has charge 0, so this cannot help, okay, right away. G12 has charge -1, so 2 powers of G12 does the right job, okay, of matching the charge of the U1 charge, but of course also add this other charge here, okay? It also adds the U2 charge. So you can have G12 square. This matches the Q1 charge, because -2, but it screws up the 2 charge because. But this you compensate now by adding G22 star, okay? So you can have something like that. And so now you expect that there is, so this is something that respects selection rules, dimensional analysis. This is dimension 0, 0, 0, they all have the same dimensionality. In quantum mechanics, if something is possible, it must happen. This is the totalitarian principle, right? I mean, you're on the top of a hill, the hill is there, you're there, you can fall. No, I don't fall, you fall. Yeah, you fall, okay? So quantum physics explores all possibilities, okay? Maybe in some cases with small probability, you have to tunnel, but quantum mechanics. And if a contribution like that can exist, it will exist. And in fact, it does exist. And you can see it already in the energy effective theory, because it comes from diagrams in the energy effective theory of this type. One, there's an interaction here, there's a vertex, okay? The vertices are 1, 2, and 5. Okay, and then there are the vertices 2, 2, 5, right? And then you get something like this. You do 1, 2, 2. Okay, this is something like this. Okay, so these are by spinors. So the UCAV interactions are all going in or going out, depending whether it's nu or nu-bar. Okay. And that's it. This is G12, this is G22 star, and this is G12 again. And that's precisely this. And you can compute this diagram, okay? And the result is that, in fact, in the low energy effective theory, if you now consider the interaction between phi and 1, 1, if you consider the phi 1, 1 vertex, the true 1, 1 vertex, this will consist of, at first order in 2 contribution, this loop here, plus the original, the one that you had in the beginning, okay? G11, which may have been very small, okay? That's a different question, okay? And then you have higher orders, but at least if this is small, this at certain point will be bigger. In a sense, what you get is that G11 effective is equal to what? And now, of course, this diagram will depend on the external momenta. Let's assume the momenta, external momenta are of order P, are of order some E, okay? This is like some vertex where all the momenta are large, okay? They're of order E, they're generic, and what you get is that, okay, what is this? This of course gives you, guys, let me do it this way. This one here, give me G11, the G11 that comes in your Lagrangian where the theory emerges from the UV. And this diagram here is ultraviolet divergent, okay? And is logarithmically divergent because these are all dimensionless objects. You're using dimensionless coupling to normalize the dimensionless coupling, so you get logs, okay? And the log is gonna be some log of the UV cutoff. You really this is logarithmically divergent in the UV over the energy of the external legs. And then you will have some coefficient of order 1 that it's the standard that you do in QFT1, okay? In Lusanne, we do it in QFT3 because I'm giving the other guys, so you already see the speed of my teaching. Okay? It takes 3 courses to complete the loop. Okay? So you can see over some 16 pi square times the vertices G12 square, G22. And now you have a concrete expression for the effective value of this 115 vertex at energies that are in the regime of the effective theory, let's say much below lambda. And you can do two comments here, okay? There are 2 comments you can make here. If you go to energies of the order of lambda, just at the very edge of the validity of the theory when it starts working, essentially what you're doing, what this diagram is doing, see, because in the contribution, very much like for the pion before, the contributions that you compute in the effective theory that are at virtualities of the order of the physical cutoff, they are essentially of the same order, the same type as the contribution from the physics at the cutoff. Is this understandable? Okay, like for the pion, we did it before, we get that lambda square contribution to the mass, which is precisely what you get from above. So the near end of this log, in the region where E is of order lambda, that gives it just consists of a piece of the UV contribution. So in other words, you should expect this G11, which is what is the UV contribution, to be precisely, to not to be smaller than that, okay? Is this clear what I'm saying? So these are, and or if you want, in the, right, and in fact, when you change, if you want, if I change the scale E by, around lambda by a factor of 2, I'm still in the region close to the cutoff. So these are just changes on scheme in the matching between the UV and IR theory, and the change in the 115 coupling is precisely of this order. Okay, so so what you expect is that in this range is that so this G11 should be not less, bigger than precisely this, which is G12 square, G22 star, over 62 square. So that's the typical expectation that you can have for this. Okay. Oh, of course, you can go, if you go to lower energies, okay, then you may be in a situation where if this of this order, then you're dominated by the running. Okay, you're dominated by that. But a situation where anywhere G11 is less than this, if you look at this formula here, can only be achieved at some specific E. Imagine there is an E for which this cancels, okay, let's say at some lower E, but as soon as you move away from that particular energy, which is like tuning, which is like asking your lab technician to tune the energy of your experiment, as soon as you run away from there, G11 is bigger than that. Is that clear? Okay. In other words, you have 2 contributions. Okay. This stays constant, this changes with the energy, but besides a specific point, okay, if you take a generic energy, G11 is bigger than that. Okay. Is this clear? Okay. And so this is so if in fact it doesn't even make sense to talk about if you really think about it. If you now go to low energies, okay, and say, oh the G11 of my experiment, I did an experiment and I got the G11 was 0. Then they say, wow, this is amazing. It means that you've done an experiment which is very crazy, peculiar energy where these 2 contributions match. Which is a because now you see, now you have another parameter that looks like the pressure that you can choose for this. Because the G11, because of this equation, as a function of energy, let's say that this one is negative, okay? When you go to lower energy, it grows, okay, starts negative, and at some point it crosses zero. But other than that, at all generic values of energy, it is bigger than that. Okay. So the natural situation is this. Okay. And there's not even a sense in saying that this coupling, this G11, is small. Another way to say it is that G11 can only be small at some energy scale. At some other scale will be bigger or small or positive or negative by this amount. Okay. So this is even more than naturalness. And the other example I want to show you is this. Okay. Let's say I have d by 1. It's a theory of two scalars. And this theory of two scalars, let's say that they are masses or where at energy is much bigger than their mass. Of course, the mass is an issue, okay? But let's forget the mass for a moment. And let me just consider the couplings. Let me consider the couplings. Here we have, let me consider this coupling. G11, which is phi 1 to the 4th, plus G12, which is phi 1 squared, phi 2 squared, plus G22, which is phi 2 to the 4th. Now, these scalars are real. Okay? These scalars are real now. I claim that G11 satisfies a constraint similar to the one before. Okay? In other words, you can there are quantum corrections to G11 that lift it above. So G11, I claim that G11 should be bigger, is generically bigger than G12 squared over 16 pi squared. Okay? And to explain why that is the case, I'll do it after the break. Now, this Lagrangian, here the fields are real, so you cannot use chiral symmetry like before. So there is another symmetry that controls this. And this symmetry is important because it's also what is at the basis of the usual results in theories beyond the standard model for the relation between the mass of the Higgs and the scale of new physics. This is why I want to discuss that later after a little break.
5:15.
15, yeah, 15. Very. Oh, I forgot.
Well, now,
Yeah, we forgot to do that. So, but it just decided by itself.
I just recorded, you already stopped it, right?
Yeah, it stopped it.
But I just started now.
Oh, okay. So then when you turn on the interactions, the interaction term in the Lagrangian can be viewed as parameters that transform under the symmetry. Okay, now if I have a I now start turning on, let me just check the way I do it. So for instance, imagine I had a quartic Lagrangian, so I have L is 1/2 phi square minus d square minus m square phi square, okay, and plus I add a quartic coupling phi to the 4th, okay. So now I can view, I can write this in momentum space, okay. Momentum space, this is going to be equal to d let me just d omega 1 by omega 1 dp1. Okay, let me just write dp1, dp2, dp3, dp4, lambda delta 4 p1 plus p2 plus p3 plus p4. So that the momentum is conserved. So I'm just writing this in Fourier space. Phi hat p1, phi hat p4. Okay. Of course, in momentum space, it acquires this less appealing form. Okay, it's a way longer. Okay. And now the effective coupling, if you want the momentum space, is this object here. Okay, you can view this as a lambda of p1, lambda hat p1, p4. Okay, in other words, you can imagine an extended theory. Okay, which doesn't even satisfy locality, but where it's like what you often do when you do condensed matter. You have an interaction which is purely in momentum space, and the coupling is something that put together momentum p1, p2, p3, p4. Okay, so it's something like that. Or only that if we want at the end go and consider a local well-to-do theory, then this object here will have is like a field with an expectation value equal to that. Okay? You can view this as an external field, okay, which can even transform under symmetries, but in the end takes this expectation value. Now, if you treat this now as an object with the same game that we have been playing so far, as an object that form and transform under symmetries, you can restore this the original symmetry. You simply have, you can formally just have to formally impose that lambda p1 p4 transforms as e to the minus I theta p1 plus theta p2 plus theta p3 plus theta p4. Because that will compensate that. Okay, so formally I can have that. Now, it's precisely this formal transformation property that dictates how lambda can affect other physical quantities. In fact, if you see in a moment, we'll see in a moment, this symmetry is precisely what tells you which Feynman diagrams you can have and which you cannot have. The structure of Feynman diagrams corresponds precisely to writing all the terms, all the polynomial terms that satisfy this symmetry. Okay? So in the end, you can say, oh, but you have wasted all our morning telling us these things and all that. This is just, the goal is rhetorical, if you want. I just want to show you that all behind this contribution, this computation you do in quantum field theory, the bare bone of the structure of the computation, the structure of the series, or the form of the contribution you get, is just as conceptually follows the same rule of the thing that you computed the first time you started doing physics when you computed the frequency of the pendulum. The conceptual ingredients are exactly the same. Dimensional analysis and selection rules. Of course, dimensional analysis is always the same. Selection rules can become more sophisticated but in the end, and associated with symmetries that are. By the way, I should say that the existence, in a sense, the symmetry I'm writing here, which are called, whose charges have higher spin, the symmetry, when you integrate the corresponding current on the fixed time surface, here the momentum gives you 4 charges, which are the 4 momenta. This next object that you have in free field theory, the charges are a tensor, symmetric tensor with 3 indices. It's the highest spin charge, and so on and so forth. Okay, and this, in a sense, and these charges transform under Lorentz. So these charges do not commute with the Poincare group. They are an extension of the Poincare group. So free field theory is actually a theory where the Poincare group is extended to an infinite algebra. Okay. And the price to pay for this big extension is that the theory is as trivial as hell. It's free, okay? There's no interaction. And this connection between the existence of the presence of an extended symmetry, or a symmetry extending Poincare, and the fact that the theory is free is the basis. It's not exactly the same, but it's the basis of the famous Coleman-Mandula theorem, which states that in a well-to-do interacting relativistic quantum field theory, where the S matrix is non-trivial, particle interact, there are no extensions of the Poincare algebra that you can think of, apart from supersymmetry. Okay, that's the essence of the Aglo-Lusanne-Tosonius-Mandulla theorem, and the essence is this: that all this additional, the symmetry that extend the Poincare group are in the same variety, and they strongly constrain the structure of the endpoint function, particularly reduce it to just the two-point function. So now, with this thing in place, the computation of what goes on here is simple. Okay. First of all, okay, I claim that this is the result, and of course the practitioner way to infer that is say, oh, come on, if G11 were small, look, you're telling me G11 is small, okay, but small, but the phi1 enters in this interaction, so quantum corrections, loops like before, will give rise to an effect that plays the role of G11 that looks like G11. In fact, if you take this interaction here, and you put 1, 1, and then you compute a loop with 2 and 2, and then you close back, okay, a diagram like this, where this is this is G12, G12. This will give you a contribution to to the 4-point function, 1, function, which goes like G12 square, some coefficient of order 1, 16 pi square. There are two propagators, so you also get a log, very much like before, like this. Okay, you also get that. And again, like before, we can now say that the effective 1-1 coupling, okay, effective at some energy E, is going to be the original one, the one that was given to you right at the beginning when you were at high energy, plus the result of quantum fluctuation, at least the first order, which is this here. And very much like before, now it's hard to argue that the 1-1, the 4-point vertex of 1-1 is small. There are two contributions. In order for that to be small, you need a cancellation like that. That cancellation can only happen at a specific value of the energy where these two guys compensate. But other than that, this will always be at least of the order of this, okay, which is precisely what happened to me. Okay, and this, which you can say, oh, but this is you're doing a computation. Who knows? But well, I'm just saying that there is this result here as somewhat more dignity than just being some random result, is a result which is enforced and unavoidable because of symmetries. Okay, and the statement here is simple. Okay, when you now turn on, when you now consider the symmetries of free field theory, you have two fields. You consider two rephasing in the let me do it here. You can do two rephasing in this theory. It's phi1 hat k goes to e to the I theta 1k. Excuse me?
Can someone swing the camera over? I think you got to hit 2.
Yeah, I'm not sure. I'm getting to
The camera operator left.
Yeah.
Oh no.
Should we press something else except 2?
2 and enter.
Oh. Oh.
That worked great.
Okay, sorry. So and the same thing for phi2. Now we'll have a separate phase. Okay, there is clearly one of these higher spin symmetry or phase rotation for each. Okay, because the kinetic term is independent. Okay, and now you can assign transformation properties to the coupling. In particular, G11 transforms like G11 can be extended to an object like this that goes into e to the minus I theta 11 P1 theta 1 plus theta 4 theta 1 P4 and the same thing for similar thing for G12, actually not the same, slightly different because G12 has 4 legs, 2 on 1 and 2 legs, two legs, so it's e to the minus I theta 1 P1 plus theta 2 theta 1 P2 plus theta 2 P3 plus theta 4 2 P4. G12 of P1, P4. The idea here is that G11 as P1, P2, P3, P4, these are all 1, 1, 1, 1, while this other coupling here, G12, has 1, 1 here, which is P1 and P2, and two legs here, which is P3 and P4. And so the compensation is there. Okay, so they transform with a different combination of phases. This is very similar to the chiral symmetry we had before, only that now it's in momentum space. Okay? And now, however, but notice that this phase is different for all momentum. So now you can imagine, precisely the same rules as before, of forming an object with G12 that has the same transformation property of G11. And you see, there is an action of the theta 2 phase on the P3 and P4 legs. Okay? So what you need something that compensated. So what you need is to take G12 and G12 star. Okay? So if you take no, not the G12, G12 of minus P. So you can take, for instance, if you take G12 of P1, P2, and then you just say K1, K2, these are different Ks, and then you take G12 of P3, P4 of minus K1, minus K2, okay? So these are the third and fourth, P3 and P4 are those associated with the 2 legs, okay? So now these guys, the changes of P1, P2, P3, and P4 give you precisely this object here. The 4 phases associated with P1, and instead the phases associated with the 2 legs compensate. And if you want, this is precisely what happens in the diagram. In the diagram, what you have, let's say you have P1 and P2, 1 legs, which go into 2 legs with momenta, let's say K1 and K2, the 2 particles, that again get back here. So here it's K1 and K2 going out. This is a vertex G12, this is a G12, and this is K1, K2 going in, so it's minus, and then you have P3 and P4 going out, and these are 1 particles. So, and then, so the basic structure of this product of 2 couplings is the one that reproduces this diagram. Of course, in the diagram, you will integrate over K1 and K2. You have certain propagators that tell you how to sum over those, but the basis, the reason why this diagram is possible and why this contribution exists is precisely associated with the way G11 and G12 break the symmetry. Okay. Is this clear? Okay. So in a sense, there is a symmetry which underlines which Feynman diagrams you can have and you cannot have. Okay. It's not just, of course, finding out the Feynman diagrams, you can just try and write them down. Okay. Another way is abstractly, writing the Feynman diagrams is equivalent to finding all the possible monomials that transform in the prescribed way given the external legs you have. Okay? Is this? I want to tell you why this is important, but so now Yes.
So in both examples, like if you, the cross quartics or like the cross couplings, they're special because they're always like multiplicatively renormalized, I guess, right?
Right, because to renormalize them, yes, because they have there is like a Z2 symmetry because they transform under right. They have like in the neutrino, it's very simple. They're charge 1, the other are charge 2. So I can consider a symmetry where for instance nu1 goes to minus itself. That's the only the G12 changes sign and the other don't. Yes, you're right. Yes.
So that, yeah.
I
so
forgot to say this. This goes without saying. Yes.
Right. So I think initially when you were saying like you isolate one like GI1 and that's expressible in terms of all the other G's. I guess this cross couplings they sort of
there are couplings
exception.
there are couplings that are you're completely right. Okay. There could be situation where the thing on the right is the coupling itself.
Right.
And then when this goes to it's like for the electron mass in QED. It's a very good comment. Yes, you're completely right.
Can I ask a question?
Yes.
So in this example that you just gave, so there's also another symmetry of the free theory, which is phi1 rotating into phi2.
Yes, you can also use that.
And does that give you more structure or not? Or it's the same in terms of
I don't think so.
exactness?
I don't think so. I don't think it gives you that much more. But it's a good question. I don't think so. Yeah, I haven't thought about it, honestly. I haven't thought about it. You mean, sorry. Sure it does. Okay, so no, it does. So there's an isospin symmetry here. No, sorry, not the vector, of course it does. Yeah. Of course. There's an isospin symmetry, and you can also view these G's as tensors in isospin space. And then the effect of loops will be controlled by these tensors, and in some situation, knowing a leg is something with a leg which has only once, you can deduce what, you do the computation, and by the symmetry, you can deduce what the expression is for 2, but it's just remapping this into that, okay? Because these are mapped into one another. You see what I'm saying? So, yeah. So for instance, if you compute the scattering 1, 1 into 1, 1, and 2 into 2, you exchange 1, 1 with 2, that you get the same result, right? Yeah, so that's actually useful.
No, but I'm saying in terms of estimating the sizes of the couplings themselves.
In this particular case, if I'm really trying to see when this goes to 0, this doesn't seem to be, because there I'm really imbalancing. No, I don't think in that case. Now, the reason why I went through all this long song and dance is because this goes at the heart of the problem of computing the mass of, for instance, scalars like the Higgs in the effective theory, okay? And so again, we can go back. We can also go back to the case of the pion we had before, okay? Remember the pion mass, in a very way similar to this. Similar to this, remember you had the pion. Let's write it this way. Let me write it this way. Pion, pi plus, coupled to the photon. Okay, this is a trilinear coupling, and this is I can now extend this trilinear coupling by the same rules to some E hat of P1, P2, P1, P2, and K. Let me call K the momentum of the photon. Okay? And now the story, if you want, it could be essentially the same. You can think, now you want to understand to what extent this object E can affect the 2-point function of the pion. Okay? Pi plus, pi 0. Pi plus, pi plus, going like this, okay, the 2-point function. It's the 2-point function, so it's the momentum P that is going on here is the same as the one that's going out, okay? And you want to now to concat an expression of this E, and you know that when you introduce this symmetry, you have this going like e to the I theta. Let's say you can even think, in fact, let me put it this way. You can now think, when you turn this E, when you consider this E as an external object, which is non-zero for all the momenta, now momentum is no longer conserved, okay, because you have an external coupling that depends on position when you go to position space. So in principle, when you have that turned on, you can have also a diagram like this, where two pions of momentum P1 and P2 are entering. In other words, the momentum is not conserved. So you have two external legs, the momentum P1 and P2, which are not equal and opposite. And what can match? What expression of E can match something like that? Well, you need, well, E has as one photon leg, you have to compensate for the photon. So there's going to be some E of something, K, and E of something minus K. Okay? So this is the thing. And then you have to compensate. So this compensates the rephasing of the photon field, and that already tells you that you have emitted the photon and got it back. And then you have to compensate the other guys here. This could be, for instance, P1, this could be P2, and this could be, well, now you have to match everything else, minus K, and well, this is going to be some P3 and minus P3. And this is nothing but this diagram, okay? There is P1, P2 here, and this is P3, and this is K. Going out from here there are P3 and K going out, and here they are absorbed and going like that. And again, so you expect in a theory where you turn on the coupling, there's going to be a contribution to the two-point function, in particular, the two-point function goes like E squared, okay? So when you go back to this equal to simply delta P1 plus P2 plus K E, this is just going back to the usual coupling, so you got a contribution to the two-point function goes like the coupling square, which is, of course, this diagram, and in particular to the zero derivative part of the two-point function, which is the mass of the pi plus square, there will be a contribution that goes like E squared, which is precisely this, and by dimensional analysis, there is the only other scale you can have in the problem, which is not adequacy. So what I'm saying, again, the fact that the pion mass that we got, of course, there's also 16 pi squared, but this is a bonus if you want to be clever, okay? There you go. But again, the fact that the mass of the pion that you compute there is a coupling times a scale square is, again, can be viewed also in this other way, okay, in terms of the two crucial symmetries here are E here is the higher spin symmetry of free field theory, which is lifted to an exact symmetry when you treat the couplings as object transform, and dilatations. So these are, again, another way of seeing things. And again, this formula seems really unescapable, okay? If the symmetries that under which the pion mass transform are broken by the presence of a scale and by the presence of this coupling, this will happen. There will be this contribution. This is unescapable, and each and every term, the fact that it's quadratic in E squared, the fact this is all symmetries. You see what I'm saying? And the same situation arises, if you want, in phi to the fourth. Okay, take phi to the fourth theory that we have here. Okay, which I've written here. Oh, now you have this object here. When you turn on the quartic coupling, you say, oh, now I have this object here. Can I correct the two-point function of phi? Well, you can, right? Because the two-point function gamma p1, p2 must transform under the symmetry into e to the minus I theta p1 minus I theta p2 of itself, gamma p1, p2 under the symmetry. And when you turn on this object here, well, you readily have an object which is lambda p1, p2, and then you say minus k plus k. This k plus and minus here compensate here and here, give you and give you something where you only have these two phases and these guys are gone because this is k and this is minus k, and the phases for equal and opposite momenta are compensating because they're equal and opposite, so you get, you get this. And what is this? Well, this is just the following diagram. You have P1, P2, and then you have a loop closing onto itself, okay? And then it means that, and what is this? Well, this is a correction to the mass. And what is the correction to the mass? Well, the correction to the mass of the scalar is therefore proportional to the coupling because of this symmetry, okay? And the scale, okay? And of course, this is a loop, so there's a 16 pi squared. So in a natural situation, you would expect this mass to be not bigger than that. Now, we have seen the Higgs. You know what this lambda is? You can tell me what this capital lambda is. Okay, what is the scale that saturates the naturalness for the Higgs in the quantity? Yeah, it's one. Yeah, it's order between 1 and 2 TeV. Okay, so mh equal 125 GeV, lambda h is equal to whatever, how you normalize it, something, okay, 0.1 something, okay. It tells you that naturalness for just the Higgs quartic implies that the scale which saturates this contribution just symmetries, right? Dilatations, assuming that the standard model ends at the scale lambda, which can be, I don't know, between 1 TeV and the gut scale, okay? Like in all other examples, like in QCD, like for the pion, precisely like for the pion, we do precisely the game, and we say, if it works for the pion, why should it work for the Higgs? And you deduce that the scale here should be below 1, 2 TeV. In fact, if you take into account the top you cover is even less than that, but that we will discuss tomorrow. Thank you guys, sorry for, and thank you for being patient. Thank you. Any questions?
So, I have a philosophy question, going back to the philosophy which you raised. So, you had the little gi as functions of capital GA, no? And originally you phrased the naturalness criterion in terms of those functions. Yes. And then you said, well, let's find an equivalent purely low energy criterion.
Or at least a
similar sounding.
A subset of this relation, because that's
exactly. Now suppose that these relationships, so between the GI and the GAs, are natural in the sense that you said, but suppose that the GAs themselves are unnatural. Suppose that the high energy couplings have some fine-tunings. Okay. Now, in the examples that you gave us, that's not even a possibility. Meaning, the examples that you gave us, purely low energy contributions to these low energy couplings obey naturalness. So these two criteria are not quite the same.
right. So the question is how. You see.
Is my question clear?
Your question is very clear, and I'm trying to think of a concrete example. And the only concrete example I can think of have to do with marginal couplings, okay? And but maybe I can imagine a theory that has two relevant parameters, two masses, and but you see, this is becoming the same as. So if the unnaturalness is at the level of the marginal, that's unstable. It evolves logarithmically, and then it's becoming a problem at low. At the end, they all boil down to fine-tunings at the matching scale, I think. You see what I'm saying? I don't know whether I'm being clear. So So for the marginal couplings, everything is in motion, right? Is it clear? Everything is in motion, and everything gets normalized according to naturalness, precisely like in the logarithm. It could be that at the point lambda when you freeze the RG and you match, there is some accident, but that's it. That's the tuning in the. If this tuning happens before, say 100 dB above, then nothing will remain in the photon because then it will be undone.
Yes, but then
If it is a relevant mass, then again, even more so.
But then your original phrasing in terms of these functions, the fundamental parameter, is not really the point, no, or not?
No, I mean, you have some, there can be accidents. I mean, of course, if you have a very precise experiment at high energy, you will see the accident because a very precise experiment at high energy is a low energy experiment. I don't know whether I'm being clear. So maybe I'm not understanding the question.
Alberto, can you repeat?
I have a very concrete, see, I think QCD makes it very concrete, right? So I think the problem with this question is that, as you said, if you view them concretely, they are much more clear than if you think in abstract. So what would be a concrete example?
Well, I don't know, but what would
Yeah, but it's okay. It's a good question, then it's a question.
Because in the examples that you gave us, you never brought up the relationship between low energy parameters and microphysics parameters. Right?
In what sense I never brought up?
Well, I mean, because you only do the computations involving low energy parameters and never expressing them in terms of the more
For the
fundamental.
pilot I did. I gave an example where we know how to do it, right?
Yes.
And then I presented also the perspective from low energy and showed that they are the same in the end, in that particular case. You don't miss anything. So the statement that, oh, we cannot talk about the hierarchy because we only have low energy, given that all that matters in these issues is selection rules, I think at low energy we have all the selection rules that we can use. The thing we may be missing is symmetries that exchange IR and UV degrees of freedom. Now we're getting into a different question. This is all within the EFT paradigm. There could be situations where maybe there are symmetries that mix UV with IR. And then these symmetries are clearly visible in an effective theory description. Again, do we have an example of that? I think what could break all this logic is the presence of.
Well, we know for gap ghostones, the non-abelian symmetries are like that, you know, but that's a
No, I think there is more like that. The effective theory is missing some of the symmetries, right? But
Yeah.
very much like the Lagrangian misses that there is baryon number. Because all the baryons are heavy, I integrated it out, I don't know that there is baryon number.
But
There is the symmetry, right?
But in the fundamental theory for the gap ghostones, the non-abelian symmetries mix the gapless and the gapped ghostones. So they do act on the gapless fields, but only also if you also have the gapped fields around. Otherwise, there's no purely low energy implementation of the symmetry.
No, I understand, yes. Yeah, if you cut off some frequencies, then you cannot define this thing. Yeah, you're right. And there's no, and this is an example you're saying.
I don't you have a paper about that?
Yeah, but it's not. It's my paper, but it's not relativistic. This is the thing, right? It's not relativistic theory. It's a theory without Lorentz values. Okay. Thank you. Now I think I'm a bit behind. So what I can do is to tomorrow and the day after to just use slides. That's probably the best way to. That's the only way. I had prepared a long discussion on compositeness, but at this stage Yeah, I mean, doing at the blackboard takes much more time than with slides. So I was able to do this all in 5 lectures, but it's clear that the material for, I should have done, longer lectures, but then it would be exacting on the students and on the public. It just forcing people to be there, hearing a guy mumbling the whole day. They have better things to do probably. So I think they probably go to slides. No, it's not.
As maybe